Awesome. Hey everyone, my name is Dan Garau. I am head of partnership engineering here at FiftyOne, working with many of our great partners across many different industries, including healthcare, to help bring the latest and greatest to both the open source as well as to researchers in labs and enterprises across the world to get their best hands on what is that open source models developments, specifically today for synthetic data. We're going to be talking all about how you can scale healthcare AI with these new synthetic data models or world models, talking about how this relates into the new ideas of things like physical AI, with a lot of awesome work coming out of places like NVIDIA Healthcare recently. Really excited to bring you with this. Been working very closely with a lot of people in the open source community as well as NVIDIA over the past 2 years or so. And really within the last month or two has been some really astounding updates. So I'm excited to share with everyone how they can get started on all this stuff today. So what are we talking about here today? Well, it's probably not a surprise for everyone here that there is a rare pathology problem inside healthcare AI today, right? I'm just grabbing here from chest X-ray, a very popular data set that maybe everyone's seen, where even when we look at this case and we have 100,000, different samples we might be training our models on, well, 60,000 of those are going to be no finding. And in the case of, let's say, hernias, that only makes up less than 0.5% of the data set. So how do we train models for this data that the data just doesn't really exist in the way that we would hope it to, right? Even here on age, we might need to translate to age, pathologies. There's many different scenarios that we're trying to cover that we want to make sure that we can train our models on. And sometimes this isn't even just actual patient results, right? Sometimes this is different types of robotic arms that we're training on, different types of medical imagery machines that we might be training on, that we might just need to fill in our gaps. Well, let's first talk about how we got here and what does the state of synthetic data look like in healthcare today. We'll be walking through some high-level slides here as we walk through my talk, and then we're going to some real examples at the end. Well, right as the boom of computer vision is happening at the beginning of the 2010s, we find very quickly that there is a large labeling or really data-starved bottleneck, right? What was really great is that NIH put out chest X-ray with 112,000 samples, 112,000. But the issue was that, it just kind of showed what was possible, and we realized how far we were behind on all the other data sets. On top of this, there's a lot of politics in healthcare that we don't always see in other different fields, both for good reasons as well as for some greedy reasons, where data is not being published every time to be easily available in open source, right? Of course, we need to think about patient de-identification, privacy concerns, as well as there's just a lot more kind of money grabs at data set is what it seems like sometimes in the field, preventing people from having these large scale data sets available to train models on. As we continue throughout the decade here, right around 2018 is when we first start seeing GAN-based augmentation being done in healthcare. In this case, we were doing GANs on tiny liver lesions to kind of create more dataset diversity and saw some initial positive results. But it isn't really until we start seeing diffusion breakthroughs, 22, 23 area, where we're really able to now kind of explode out the amount of synthetic data that we can have, and it's actually making an impact, right? We found that there's multiple different ways to kind of control these diffusion models, especially for tasks like chest X-rays. And hey, maybe I need to synthetically add in a pacemaker, right? It's a great example. What we found out that very easily we can kind of use things like diffusion models with control nets, guide them with the correct prompt, and that you're able to get pretty high quality results that resemble real patients with maybe a pacemaker and a pathological finding as well. This advanced even further within the last 2 years with really the launch of very large as well as these world models. NVIDIA MISE and NVIDIA Cosmos are two that really come to mind here, where these are specifically surgical world models, trying to help push out more synthetic data, not from just a standard image diffusion, but also for video as well. And now we're really starting to see the first real world impact of papers coming out recently that show that there's this new paradigm of synthetically pre-training your data on a bunch of different synthetically produced, sometimes entirely synthetic, sometimes synthetic augmented data, and then fine-tuning this on real data to get a significant performance gap, allowing you to really close the gap where previously we didn't have the data to do so. And what's really great about some of the studies that we'll be looking at here, we're not going to be diving into any of them deeply today, but we can show that not only were these showing that, hey, synthetic pre-training is a great method, but that we're also showing that the difference between if we just did this project with real data versus if we had synthetic and then less data that we're training on, and what are the results between those two. So you can kind of break this up into three different ways that we've been working on it. Kind of previous, kind of what is maybe currently in production for some people, and now what is happening today. The first one is this kind of Roent gen, where we're doing kind of stable diffusion plus a control net. I just picked this one, but there's many different flavors of this, especially for different types of medical imagery and pathologies that you're interested in. But basically, it's taking that classic stable diffusion architecture and then text conditioning it to be a new pathology, to add in that pacemaker I was mentioning. Maybe you're adding in other medical instruments, whatever it might be. But this is a controllable text image to image type generation. It showed that, it did improve results on a lot of tests, and that for a lot of these basic kind of chest X-ray type augmentations or generations, it was barely detectable as synthetic. Afterwards, we got a little bit better where with NVIDIA and MICE, we're now doing this not just on images, but as well as on CAT scans and 3D latent diffusion. Similar architecture where we're using a diffusion backbone with a control net, but now we're not doing it on just images like X-rays, but we can actually do these on CAT scans and MRIs. We're doing this across large amount of segmentation classes. We did this, the NVIDIA also trained this model with something called Vista 3D, which is a auto-labeling segmentation model that came out of this work. And basically, it just outputs the voxels. And we also saw that this was increasing the performance on tumor segmentation inside of these CAT scans and MRI tasks. Still not significantly large jumps, 2.5 to 4.5%, but still a big jump nonetheless, right? Any type of improvement will take, especially when it comes to saving lives. And then lastly, within the last, I don't even want to say year, but really kind of 6 to 9 months or so, is when we're finally seeing these world models, right? And not to, bug everyone down with kind of world models and, new buzzwords and things like that, but the idea of these world models, unlike the latent diffusion models, is we're trying to bring in much more physics accurate information, both at the pre-training side as well as on the inference side in some cases as well. No longer are we just kind of latently diffusing until it looks like something sometimes. We can actually pass in some real world information. We're training it on a little bit more physics accurate information to hopefully get a little bit more of a structured output. What's really awesome about some of these surgical world models is we can pass it in just a single image, and then it will actually predict forward a video based on a task. You can condition this with actions, you can condition it with text, and it really has started to now outperform real data only policies on certain robotics, right? So for these tasks that have very minimal data, if we can synthetically generate a large amount of data for pre-training, kind of get the model ready, conditioned of, hey, this is how surgeries work, and this is how lesions work in this part of the body, and this is how we make incisions and such, and this is what it looks like, right? Even if it's synthetic, it's not going to be maybe 100% accurate, but today it's pretty close. And then we fine tune this on real data. We're finally getting to a point where we're having a very reproducible workflow using synthetic data, using these new kind of world model models coming out of academia as well as NVIDIA. For full clarity's sake, all these models that are coming out of NVIDIA and everything like that as well are completely open source, right? You can go onto Hugging Face right now, download them, and start using them today, right? As well as a significant amount, if not all the data sets that they're training on are also open source, and they're very open about what they're training on, and you can take some of those videos as well. So how does this work? Does it actually work? Well, here's the evidence that we have so far. Well, we kind of go back on the original chest X-ray, And we saw a little minimal improvements whenever we were using these kind of older diffusion-based methods or GANs. However, as we kind of move to the more recent scenarios here, the synthetic pre-trained plus real fine-tuned method is showing actually improvements anywhere from 6.5% to 10 to 20 points in certain dice locations for these ultra low data regimes, right? So I know a lot of metrics flying around, but basically across the board, as we seem to be getting better at the synthetic data generation, as well on top of this, kind of figuring out what the right workflow is this, right? It's not a matter of just producing the data, but how do we incorporate the data into the training process with the right prompts, making sure we're only using data that's not hallucinating, and so on and so forth. We're slowly but surely picking up steam in the field to have real significant impacts on the models that we're developing today. The key finding here that I want to emphasize again is this synthetic pre-trained to real fine-tune method, right? This beats better than just real synthetic mixing. It's better than just doing just real data on a small amount, right? And with all the different studies that are coming out of this Stanford 2025 study, it showed that when we check all the different metrics, we're doing very good. However, we still can't do just synthetic only, right? We can't just start from zero and go all the way synthetic. We're not quite there yet. We're still going to be behind on 5 to 15% of scenarios, but I imagine a lot of this is going to close, and we still should never give away the value and understate the value of real data, right? But this kind of idea of pre-training on a really, 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 really large amount of data and then just fine-tuning on the ultra low data that you have is seeming to be a pretty good recipe so far. So how does this workflow work in production today? Well, you're always going to start with your real data. I just listed a couple popular data sets there. It can be a DICOM, it can be a NIFTY, it can be an X-ray, it can be a video, right? Doesn't really matter. We have methods now for each one of these. Then you're going to want to pick the right generator for you, right? We have some classical ones, but we have some newer ones there as well. And this is really just how are we going to get data and kind of make it more robust. Sometimes this is creating synthetic data and blowing up 100,000 of them and making sure we have a huge pre-training lake to touch some. Sometimes this is using things like Cosmos H Surgical, where you can do things like Cosmos Predict and Cosmos Transfer, which we'll be looking at in some real examples later, where, hey, we can take these kind of videos and augment them to be a different type of robot arm, or we can augment it to be a different type of bleed that is happening. We can make it a little bit darker depending on the lighting situation. We can also use this to predict out multiple different futures based on a certain prior. Another one, I don't really have enough time to talk about it today. I just want to call it out. A really interesting paper that came out of Johns Hopkins recently, I believe it was published in MiCai, is this idea of, I want to call out that there is this whole other field that is happening at this time that's using generative AI, not necessarily for purely synthetic generation like this, but taking LLMs, looking at medical reports, as well as the ground truth scan, right? So we have the scan, we have the report that the doctor wrote up. We don't have annotations and segmentations because no one took the time to actually manually annotate them. But now with LLMs, as well with some fine-tuned segmentation models, depending on the organs you're interested in, we can actually take medical reports, the CAT scan, some open source available models, and generate really high quality data sets using this. And so really interesting work coming out of Johns Hopkins as well as a couple other groups there. But really all this comes down to is how are we creating the best data set possible, right? We want to use not just the real data, but take advantage of all the generative AI and synthetic data generation and world models that we have available at our disposal to make this best pre-trained and training data set. From there, the next most important stop is going to be curation every time, right? Because if we are trusting the synthetic data that we just maybe generated 100,000 videos of, we need to ensure that we aren't hallucinating in any of these, right? And there's many different ways that we can talk about this. One is very similar to the paper that we just listened to, or the work we just listened to, is embedding-based gap detection. This is going to help us find outliers. It's going to help us find scenarios that are very similar. It's going to help us identify if there's a sim to real gap. And there's many different techniques, both PCA as well as UMAP and other different ways to understand if there are any gaps or outliers inside of here. We want to make sure that we're not just training on, the same data over and over again. One of the unfortunate downsides of synthetic data generation today is sometimes with a similar prompt or something like that, it kind of defaults to a sample similar to it in the training data set. And so you're going to get a lot of outputs that look just very similar. And I'll show you some of these examples where, I'm not personally doing surgery in the OR or anything like that recently or anytime soon. So I can't really tell the difference between one surgery video between the next because the model's kind of just predicting the same video over and over again. We also want to make sure that we're auditing the fact that we're not just moving and drifting the distribution away from something, right? If we have a problem we're trying to solve, we have the real data that's there that's trying to be solved about it. We want to make sure that we are able to stay on top of the problem and not accidentally drift away when we're doing this large batch of synthetic data. So curation and QA is absolutely important before you do any large-scale training. Afterwards, you finally get to this downstream model where you're going to do that pre-training fine-tuning loop. Um, there's been a recent shift to be a little bit more per pathology based, right? I don't know what the change was. I think it was more accuracy based, where personally, out of a lot of the large scale Gen AI kind of either auto labeling or models that are being developed, they had a lot of zero shot or we'll look for all the problems. Now we're doing much more organ based or specific pathology based. Regardless, just make sure that you are being fair and always checking your subgroups whenever you're doing any type of analysis afterwards, right? So if we're doing this whole training process, we can hop back into a tool like FiftyOne and say, hey, it's well and good if we're 99% accurate, but are we also making sure that we have, covered all of our different subgroups? How are we doing on patients under 50? How are we doing on patients that have multiple pathology findings? Whatever it might be, all this is possible and should be done after the training loop. We're going to walk through this kind of workflow live in a second here, but we're always going to want to ingest and inspect your data. I'm going to show you a really awesome way and kind of focus a lot of my time here to make sure that everyone can get started with their work very easily. Then you can run embeddings. We actually have some built-in embeddings into the FiftyOne Zoo for medical imagery, so you don't even have to worry about bringing your own model. PubMed and Biomed Clip are available for you to generate embeddings on you there. And I'll show you how you can do that even very easily using our enterprise tool. We want to then detect any gaps and similarities that we find. I'll show an example using chest x-rays. Then you want to generate or inject any synthetic data that you're interested in. Once again, I'll show you a very easy example using Cosmos H. Afterwards, we're going to audit the quality, make sure that there's no duplicates, make sure that there's any flagging. I'll show you some of the manual annotation possibilities inside of Foxel 51. And then afterwards, you want to do your training and an evaluation, all things that can happen inside the tool as well. Lastly, I want to touch on this is kind of how is privacy and regulation kind of caught up to this, or has it at all? Well, here's kind of where we lie today. Well, there's been 1,000+ approved authorized devices. This is no shock to everyone, right? We're just exploding in the amount of AI and ML enabled devices, both in doctors' offices and hospitals and many other locations. But so far, as of my research, only 8 have explicitly said that they use synthetic data generation during their training process. So a very small minority of the approved devices are using synthetic data today. So far, as of last year, we have to make sure that we're always reporting data lineage whenever we're doing these kind of FDA approvals, and that includes synthetic data. So you have to be open and honest about, hey, we did train on synthetic data, and so far it seems like people are pushing there, but we actually haven't had anyone push back on synthetic data yet, right? The FDA and no one else hasn't at least put out any guidance or guidelines or anything like that that says, hey, you can't use synthetic data. Just make sure that you acknowledge synthetic data. And then lastly, kind of as we move over to the right side here, of course, you can't get approval with just synthetic data. Like they're always going to want to see some real life, real world applications before they approve anything. The only other thing that there's very concerns of right now, and I agree as well, this is a large concern even before as well as especially after synthetic data, is privacy, right? These models are not against certain types of inference attacks that can identify training subjects by trying to get them to output names, right? So if a person's identification was located during the training stage of a synthetic data model, well, if it wasn't properly de-identified, then in some way and somehow it is possible for a attacker or just an accident to accidentally then leak that personal information, which is of course a huge privacy risk. So always trying to be on top of it. It's always important to do de-identification checks before and after synthetic data running. But with the correct curation methods and the correct QA and auditing of your synthetic data, I do not think that this kind of identification leak in training in any real lab, at least, is of a significant concern today. And as of right now, no large synthetic data pushbacks, right? It's green lights coming from all we can see. So where are we going? What's up next, right? Well, pushing from the end of last year and now a little bit into this year, we are pushing hard on this synthetic pre-train and real fine-tuned path. Seems like it's been having a lot of promising results. And we're seeing more and more papers popping up. Next is this agentic idea of training, right? The operating room is really getting a lot of focus right now. A lot of times we were getting, scanning in the past, right? You get the AI to look at your MRI, your CT, your chest X-ray, and hey, do we find any findings? But a lot of research and a lot of effort is actually in the operating room today, right? Where surgical robots are going to be doing the procedures in the future. How do we start training these VLA end-to-end physical AI models to do this surgery in a very automatic end-to-end and way with, of course, the safety in mind of all the patients along as well. So not too unlike robotics and unlike autonomous driving that are moving more and more into this physical AI realm, the operating room is as well. I'm going to say that I expect regulatory frameworks for synthetic data, especially as we move on. I don't think it'll probably happen in the next year or maybe the following year, but just start having really good data provenance now. So that way you don't have to worry about doing this later, right? So if you are interested in getting synthetic data, you are interested in doing research or even training models on it, just make sure you have like the prompts that were posted on it. If it was based off of real data, what data was that? All these different data provenance things. So, hey, in the future, if there ever is a more robust data audit or more robust data provenance that you're going to have to provide, it's better to be doing what you think is best now, which is very little overhead of kind of carrying over some additional metadata, than get punished later on, right? And have to pay that toll later. Lastly, curation is so important, and I can't undermine this enough, right? We are trusting a lot of these agents today. We're trusting a lot of this synthetic data to solve our problems. We need to have very effective ways to scan model results as well as our data sets to ensure that, hey, if we're training on all this synthetic data, that's great. But I want to make sure that we're not training on any hallucinations, that we're not training on anything that's going to harm someone. And having a really easy way to do that starts with having really great data curation. If you can't dive deep into your data set, if you can't find the mistakes that are happening there, those hallucinations, then you're going to have a significant problem downstream. So let me jump over. I believe I have a little bit of time left. Just kind of want to show you how you can get started ingesting some of your data sets into Voxel 51. So taking a look here, we have a couple of examples that I want to walk through. I pardon anyone if they're a little queasy today or was about to eat lunch, but we have some really great data sets that are available on Hugging Face. For instance, Collect 50 is available there. When we click into any of these, we can see the different surgery with all the different tags on top of it, with metadata from where it came from as well. We also have some examples of that Cosmos surgery, Cosmos synthetic data, both from the data set level as well as the actual running example, both available on Hugging Face as well. So in this case, we're actually taking that Collect 50 data set that we were just looking at, passing in the image, and then having Cosmos augment our data set to produce a video predicting what the robot arm is supposed to be doing based on a specific instruction passed to it. This is what a Cosmos Predict model output would look like, and we can do this for many different body parts. We pass in a specific image, we go to our predicted video, and we're going to be able to get this kind of 6-second clip out, just kind of giving it a little bit more physics of what it looked like. And of course, with different controls and different prompts and more aggressive instructions, you can have a little bit more robust movement here. However, as this is a little bit of an older version of the model, they just released a new checkpoint actually in March, which is very exciting, and I'll show you the results on the page as well. You're able to get more robust bolts with more movement and kind of a little bit more described work here, but just the first step, and it's very, very easy to work with these Cosmos models, right? You can head over to their Hugging Face page. I actually recommend heading over to their GitHub page, where I think it's a little bit better getting started. But Cosmos is super easy to work with because typically you're either passing in a video or an image and then just prompting the model out. So they have a lot of really great examples here. You'll see not too different from what I'm doing, but with even better results now than what I was using before, right? So we can change it here to have a little bit more coagulation, and you can see that they're clamping here. I'm about to have lunch soon, so I'm not going to look too much about this, but really highly recommend checking out the Cosmos models, really strong. And if you're interested in using these Cosmos models in production, check out Voxel 51's Physical AI Data Factory, where we're helping build out all of these in a very large scale way. So I'm super interested in all the stuff that's going to come out of NVIDIA in the future. They're pushing it all to open source. In fact, I kind of want to highlight one more thing before I hop off here. I noticed this morning that there was a couple new data sets that came out of NVIDIA. In this case, they released a lot of the data that they trained on for this Cosmos model. Now, this data set came out in March, and you can see it was 4.37 terabytes. I don't have that much space on my computer, and I was really interested in being able to show it to you today. Spoiler alert, I was. It's right here. Here's an example of me pulling a couple different samples where we have multiple different endoscopes left and right with all of our metadata stored on the right here as well. What was really, really exciting about this and showing you how easy it is to get started now with Voxel 51 and loading in new data sets, I actually just copy and pasted this link, and using the brand new Voxel 51 skills, I just copy and pasted it into my Claude code, said load this data set into Voxel 51 so I can start using it. And within 5-10 minutes, I have exactly what I was looking like here with 6 different images. It prompted me to say, hey, do you want some additional subsets? I said, yeah, I do. Give me some, practice clips like this one here. And we were also able to get that out. So really, really awesome stuff that is coming out of my colleague Adonai's work with Voxel 51 skills. If you use Claude Code, Codex, Gemini, anything like that, you can literally, like I said, just copy and paste Hugging Face links and instantly start working them in a computer vision context in Voxel 51, where it's super, super easy to get started with. You can combine data sets, export data sets for specific formats. Really, really strong stuff, and I really encourage everyone to check it out if you haven't already. And then the last one, just want to point out how easy it is to work with Voxel 51 and work with things like, for instance, our chest x-ray that we've been talking so much about, how you can have these very custom plots, work with it. You can add any of these plots as you're interested in. For instance, if I want a pie chart that shows me all my different pathologies, well, all I got to do is then just pick my labels. It's going to show me a little preview. I can create this plot. In a couple clicks, I can see all the different distribution of all my different findings here. And well, if I'm interested in, for instance, all my masses, I can just click on it. And on the left, sure enough, it goes from 100,000 samples down to 5,782. You can pile these on, stack multiple ones on top of it. So for instance, if I was interested in now only patients that have masses that are under the age of 45, sure enough, I can do that as well. And all of this, as you can see, is nice, snappy, and clicky, as all of this is being hosted on the cloud. In Voxel 51 Enterprise, I could copy, paste this, send it to my colleague to get a look at it, save all these different dashboards that, as you can see, are updating live every time I add any of these new filters on top of it, as well as I have embedding plots to show exactly how we were looking at it before, all the different pathologies to make sure that there's any specific groupings, any outliers, any concerns, that we can catch them before that model training time. Wrapping up here, 3 big takeaways I want everyone to walk away with here. 1, synthetic pre-trained to real fine-tuned seems to be the new default. Not going to go into any more detail. I've said it so many times, it just seems so powerful. 2, treat synthetic data as a first-class data set. It's not a gimmick. It's not for fun. It is a real data set. But with real data sets also comes real data set things, such as curation, finding outliers, duplicate removal, as well as the new one of removing any hallucinations as well. So make sure that you're really taking a look at your data set, but treat it as a real data set that you can actually get significant results off. And then the last one, I always like to mention these in my synthetic data ones. I hope that one day I don't have to. I want everyone to go home and remember that, look, it doesn't always need to look real to do a better job, right? If I have a little bit more of a cartoony or a little bit of an unusual video, that maybe doesn't seem exactly right, but hey, when I train my model on it, it does better. The end goal is to train a model that does better, right? And we want to be validating this on real data, not the synthetic data, right? But don't be afraid to do a large amount of synthetic data. It's not always going to be perfect today. It might be a little strange at times, but the results are there. That training on this data can have some really great results. As long as you're not having any like large, crazy hallucinations, it's sometimes very common and recommended to include those videos as well. So I'll put up a couple links in case anyone's interested in getting started. First QR code is to our 51 skills where you can plug this into any of your coding agents. It takes 1 second to install all these skills. And with just copying and pasting links into your box, into your Claude Code, Codex, or something similar, you can get started with Voxel 51, loading up these data sets and building up computer vision workflows. Ask questions about some next steps that you can do and more. The second one is the Voxel 51 guide to the getting started with medical imaging. A great place if you're interested in just a beginner's guide on how to get started with medical imaging in Voxel 51. And then the last one, if you have any questions that you think of after this talk or that you're interested in, there is my LinkedIn. I encourage everyone to connect, reach out. If you have any other follow-up questions, always happy to collaborate or talk about different partnerships or potentials in healthcare or other fields.